I'm sure there'll be, oops, there we go. Hello, everyone. I think we'll get started. It's just about 10 a.m. I'll introduce myself and then have Kevin introduce himself, and then we'll kind of get started with the presentation. Just some general housekeeping. If you have a question, feel free to type it into the chat, and we can answer as many questions as possible live. When I get done introducing myself, I am going to shut my video off. That way the screen's up, and then you can kind of hear audio and then see the screen. And then we'll touch base kind of later at the end. But again, if you have any questions, feel free to ask them out. If there's anything I can answer live that's pertinent to what's going on, I'll stop the presentation and just talk specifically to the question. But if it's something slightly off topic, I'll just kind of wait till the end so we can do more of a Q&A at the end. So Kevin, if you want to take a second and introduce yourself.
Absolutely. My name is Kevin Weaver, president of Brewmation. I'm just going to join the seminar just a little bit toward the end, talk about some controls as it pertains to the filter press. But otherwise, Trey here will be taking over from here.
Great, thanks, Kevin. Again, my name's Trey Senni. I'm the head of sales and engineering for MicroPure. We have been doing the filter presses in the brewery setting for about 8 years. We've been doing filter presses in other industries for roughly 40 years. And then about 8 years ago, we kind of got into the food and beverage space. We roughly have about 50 operational presses out there. Between most of them are brewing, but we do have a number that are in the distilleries, sake applications, and as well as a couple other random food type processes. So we've had a good amount of experience, hands-on and engineering wise, in the mash presses. So the gist of the talk today, we're going to talk a little bit about advantages kind of at the end. But the bulk of my part of the presentation is going to be specific to really what is the filter press, the anatomy of it, process flow. I really want to try to cover a lot of the things that I talk to sales applications for on a regular basis to really kind of give you all the basics of the press. So I'm going to pull my video off now and put the slides up, and then we'll get started. So here's the two basic shots of the press. The press on the left does not have the squeeze bar manifold on it. When we get to that, I can talk to what that specifically does. But that angle of the press does give a really good angle of what the inlet and outlet manifold looks like. So you kind of get an idea from there. You can see in the picture, if you're looking real closely, there's some black on the inside, that's the cloth. That was a real specific application we did, and that's something we can talk about when we get to it. Picture on the right is the exact same press, but just from the other angle. So it's kind of showing you the pusher plate, and then kind of a good side angle of the manifold and the squeeze bar. So the first part, the actual frame of the filter press. So we use a carbon steel frame. The two basic reasons for that are the strength of it and the cost savings. To try to do an entire press frame in stainless steel would basically price us out or price anyone out of using it and gaining the advantage from it. So what we use is a carbon steel frame. And then we have an FDA-approved two-part paint that we put on top. So that way you are safe to use it in any sort of food process. And it also then gives you the advantage of cost savings from using a steel version, but then also safety for being in an actual food grade facility. The unit is pre-treated and sandblasted prior to us painting it. Reason we do that is it takes any imperfections out of the steel, and it allows the paint and epoxy to adhere better. So you should see less chipping or things like that throughout your lifespan of the filter press. Next part, inlet and outlet manifold. There's two parts to this manifold. By using the carbon steel frame, we obviously don't want any of your brewing process touching the carbon steel. So we have to make sure that we put something in that allows your mash and then your wort to go directly from your kettle or your whatever it's coming from through food grade product to food grade piping, that we want to make sure everything it's touching is actually going to be food grade. So what we do is we install a special head plate that's made out of stainless. And so the picture that you're looking at on the left is the 5 different stubs coming out that the process would actually be going through. Depending on what type of filter plate you have, you can either have 5 ports coming out or 4 ports coming out. There's not necessarily an advantage to one over the other. It's really just what filter plate companies supply us with would be typical in what's going on. Typically speaking, we use a 5-ported plate. The one that you're looking at in the center is where the feed is going into. So your actual mash inlet would be in the center. And then those 4 on the corners are actually the returns, is where the wort would be coming out after it gets filtered. Picture on the right that you're looking at is the actual completed manifold. So like I just said before, the inlet port is directly in the middle. And then the 4 ports on the outsides where the outlet is coming, that is where the wort would be coming out. And then in the manifold, we have it tied together in a stainless piping, so that way you have only one specific outlet. So that as you're looking at it, you have one inlet and one outlet, and the manifold brings all 4 of those outlets together into one specific unit. Way on the top left of the picture, we have a valve. You can use that for sparging, which we'll get to in a little bit. Or you can use it for a blowdown procedure. The blowdown procedure isn't something that's typical in the brewing industry. It's typical in a lot of other industries, and it's something that we supply depending on whether you want to use it for cleaning purposes or the possibility of sparging from the corner. Next part is the actual closure. The unit is run under pressure. We basically take all of these chambers that would be filling up for the filtration, and then we put pressure on them to keep it closed. So that way, as your unit is filling up, you're not leaking or having any sort of issues. So these are the 2 parts of the actual closure. The first one, picture on the left that you're looking at, is the hydraulic unit. This is actually what is allowing the piston and everything to move. Inside that giant black box that you're looking at is basically full of oil. And so then as you feed it with compressed air, the oil is pushed down and the pusher plate is pushed out to keep the unit closed and under pressure. And that's what you're seeing in the second picture here, directly in the middle of the second picture. That's the actual piston that's pushing out. So everything, every time you feed it with compressed air, the pusher plate gets pushed and closes, and then if you retracted it, the air would leave and the oil would fill back up in the reservoir, and then the pusher plate would open, that you would have space in between the plates. And so this is what is allowing you to keep your unit closed and under pressure while you're feeding from the other end. So this picture that you're looking at here is on the opposite end of what was seen in the previous slide with the manifold. So on this manifold side picture you're looking at, the opposite side is what would always have the pusher plate as well as the hydraulic unit. For the most part, all of these units are basically just run with compressed air. That the compressed air is going to feed the hydraulic unit as well as the air squeeze manifold, which we'll get to in a minute. You can get into electric hydraulics or different hydraulic packages, but they're really not necessary until you get into a much, much larger press. Typically speaking, a press for a probably 30-barrel brewery would be where you would start seeing electric hydraulics. But prior to that, anything smaller, you'd be running the whole thing with compressed air, which is really nice because you can have one compressed air feed that's essentially doing all the processes on your unit, as opposed to having to deal with bringing in other utilities into the process. This is the membrane squeeze manifold. So the membrane squeeze is what is actually going to, be the second part of the process flow. Question about air consumption and PSI requirements. So let's go back. We can talk about that as we do the membrane squeeze. There's two different air consumption and PSI requirements. The first part of that, the first part of the air consumption and PSI requirements would go to the hydraulic unit. So the hydraulic unit needs about 100 PSI air, and it's not based on consumption because it's not a pass-through. So it's something that you need a specific amount of PSI air, and roughly speaking, we'd suggest you have about 30 to 40 CFM in whatever compressor you're using, but it's not something that it's actually taking a consistent 40 CFM. When we tell people 30 to 40 CFM, it's typically a rating just to help you buy the right size compressor, but it's not something that you're continually using 40 CFM. We just need you to be able to get to a certain amount of pressure. The second part of the air consumption, comes in with a membrane squeeze, which we'll get to in a later part of the presentation when we actually talk about the process flow. So membrane squeeze manifold, what you're looking at in the first picture is the actual inlet pipe for the air squeezing. You'd be feeding that with compressed air, and then the air would go into the plates and would actually allow the plates to expand as you had your mash in there, and that would actually squeeze the excess liquid out of your grain cake that you have in there. Second picture that you're looking at is a close-up of the connection from the air squeeze pipe all the way into the plate. So it's a very simple compression style hose that comes from the pipe into the actual plate. Everything's stainless, so that way it's a purity thing. But this is what does the second part of the process that really gives you the advantage for the membrane press. So now here's what's actually doing the bulk of the work, the actual filter plates. There's two style of plates in the presses we do. The first one is the membrane. That's actually to the right. The membrane plate actually expands. The membrane plate is made up of three parts. It's two faces and then an inner section. They're welded together. So like when you got it as a unit, it would only look to you as like one specific plate. The reason it's done like that is when you feed the compressed air into the side, the plate actually expands, and we'll show you a picture of that in a slide coming up. The picture on the left, is the chamber. That is the solid plate that's giving support. So the way that the plate or the press is set up is it rotates every plate. So it goes chamber, membrane, chamber, membrane, chamber, membrane, all the way through. And so as you're doing it, the membrane is going to be squeezing on both sides, and then the chambers are there for the solid support. Last part of the filter press is the cloth. You can see the picture on the left is the picture of the cloth installed into the plate, and then the picture on the right is the loose cloth that is actually installed. These are removable. There's two styles of cloths. There's gasketed and non-gasketed. Both of the pictures that you're looking at here are gasketed plates. Typically in the brewing applications, we do gasketed plates. It helps with leaking, as well as the process flow, because you get to have your feed port in the center. But there are presses out there that are non-gasketed, where the cloth essentially just drapes over the plate, and then you just have a different looking plate, or plate and cloth essentially. The question in terms of are the plates hard to if the cloths are hard to remove and replace? Yes and no. These cloths are designed to be used until they're essentially broken. So the gasketed plates, the advantage of the gasketed plates is they're much better from a leaking or loss point of view, but they are a little bit harder to remove and replace. So typically if you have a gasketed press, you would be cleaning them in place by just running a simple CIP solution or hot water through your press on a regular basis, and the cloths would stay in there. If these were non-gasketed that they're draped over, they're much easier to take off and clean, but there's a lot more that you have to do to make sure that you keep your pressure up. Typically speaking, the cloth should last anywhere between 6 months to a year, depending on how much you brew, how often you brew, temperatures, grain bills, things like that are really going to affect it. And so you would end up replacing cloths, 6 months to a year. The gasketed plates that you're looking at, those should roughly, each plate should take someone 5 to 10 minutes to completely replace. It's a relatively easy process, but if you're looking at the picture on the right, the outside of the plate, there's actually a small rope that's inside of the cloth, and that's actually pounded into a specific groove on the plate. And so then to get it out, you essentially have to use a Phillips head screwdriver or something with a flat edge like that you kind of pull one small section to get out, and then you could essentially pull the rest of the cloth out. And then you would do the same thing on the other side, and then you could put a new one in to replace it. So it's not a hard process, but it is a something that you would have to do 6 months to a year. It's not something that these cloths should not be replaced once a week or once a month. You should get a good amount of life on them before you have to look at replacing them. The cloth is actually what is doing the separation between the grain and the wort. So as we get into the process flow part of the presentation, in a couple minutes, you'll see where everything fills up in the chambers, how it goes through, and where it really goes. But the grain essentially sets up and then doesn't go through the cloth, and then any of your wort would go through the cloth. The cloths can be made in a variety of different micron levels. We have ones that we use very specifically to the brewing industry or very specific for distilleries or sake or any of those other applications. But it's always open to interpretation, depending on how you want to use your process flow or depending on what your application is. You can really choose a different micron level than what we typically use, and it would just affect your process flow or maybe your steps in the process a tiny bit. The ones you're looking at the picture on the left, this filter cloth is really tight. It's about a 1 micron. This is actually for a different industry application with like edible oils. And then the one you're looking on the right is actually our typical brewing cloth. The way it's rated with the way it's rated, it's 15 to 30 microns. So when you start the process, it'll slowly start at about 30 micron, and then the more grain you get in there, you would actually end up getting closer to about a 15 micron on the end. And then we'll talk about that in the process flow area. In terms of cleaning the filter after each use, there's 2 different types of cleaning that we would recommend. The first one is if you're brewing multiple batches in the same day of the same exact beer, there's really no cleaning in between besides getting the solids out. So if you can get the solids out of the chambers and get the solids off the cloth, you can close the press back up and start immediately filling again if you're doing multiple batches of the same beer in the same day. If you're doing different beers in the same day, what we would really recommend is a hot water wash just through the plates to essentially get all of the previous grain, enzymes, anything like proteins that could be left on that cloth. We really want you to remove, so that way it's not going to affect your future beer production. And then the third type of cleaning is if you are totally done for the day and then you're not going to use the press for a day, 2 days, a week, whatever it may be. That's when you would actually want to do a CIP cycle. Everything that's going to come in contact with the mash and wort is polypropylene, which is an FDA approved material, or stainless steel. So when you use your CIP solution, all you need to do is check to make sure that that CIP solution and chemical setup you're using is okay with polypropylene and stainless steel, and then it's okay to use on the press. So the cloths are made of polypropylene, the plates are made of polypropylene, and then the piping and external stuff is stainless. So as long as it's okay with that, it's okay with the press. We have a step-by-step valving setup that you can use to help you run your CIP through your system and make sure that you're getting every single chamber, every single nook and cranny clean prior to leaving it to dry or keeping it closed and ready for the next time you're going to use it. All right, so here's a picture again. The same thing we looked at the beginning. So now I've kind of gone through all the anatomy portions of the filter press, and then we're going to get into the process flow. So process flow is very simple. The press is designed to essentially replace the lauter ton. So everything that you're doing from a brewing process at your current facility or what you've read or researched or wherever you're at in your process, everything that you would do with a traditional setup with a lauter ton, replace the lauter ton with a mash press, and you're going to get the exact same setup. So everything that you could possibly do with a lauter ton, you would do identical with the mash press. So as you're looking at the picture on the right, the center hole is where you're pumping in your mash. There's, whether it's just a simple port there or you would have a feed valve on it, you're going to have some sort of pump that's going to be taking it from your kettle into the press. As you're filling, your outlet valves are going to be open, and then your wort is going to go into a grant tank. That's the only small addition that you're going to have to this setup. The filter press does not work well under back pressure, so you can't pump directly from the end of the press into a tank. You need basically a small grant tank or a small buffer tank to allow the press to drain without pressure into this tank, and then you can pump exactly how you want to into your next tank after that grant tank or that buffer tank. So there in the middle, you can see the feed port, and then we have the 4 outlets on the manifold all piped together going to one central outlet. In terms of the chambers flow, so and as you looked at that last picture, feed was going in the center, and then this mash is going to be filling up all the chambers. So depending on the size of your grain bill, you're going to have a specific number of chambers in the press. And so as you're looking at this, you can see the feed hole is in the center of each of these plates. This really light grayish color is the actual grain that's filling up. You can see it's labeled as filter cake. And then on the bottom right and top left there, the clear filtrate, as they're describing in this picture, is the actual wort that's coming out. So the way this works is the mash is going to come in and start filling. The mash is going to fill the path of least resistance. So it's not necessarily going to fill back to front or front to back or side to side or any specific way. It's going to try to fill wherever there's room. So normally what happens is as your mash starts pumping in, you'll fill about half of the first chamber, and then it'll slowly creep over and fill the second chamber, third chamber, going back, basically the bottom half. And then as those spaces get slowly clogged up, it'll start filling up the top half. Your goal with your fill is uniformity, that you want to get even grain across all of the chambers throughout the entire press. So when you're looking at it, when your tank is empty, your filter and all the chambers should be completely full of solids and you should be done. There shouldn't be a point where your tank is empty and you have a bunch of empty chambers at the end. That's not good for the press, or vice versa. You shouldn't have a press that's claiming that it's full by pressures, and then you still have half your tank full. That means something went wrong in the press. That it should be an even equilibrium, that as you're filling your press, your tank is emptying, tank is done, press is full, or vice versa. In terms of process, we do recommend doing a Vorloff or a recirculation. The outlet point down here on the bottom right, you would connect back to the kettle. The reason we want to do this is to help set up the filtration bed. What we've found in terms of cloth selection, speed, and efficiency, is that we choose a little bit more of an open cloth than maybe what you would typically pick to get your wort clarity. And you run a certain amount of your mash in to get it set up across the bed. So that way, not only is the mash acting as a pre-filter, it's evenly setting up, and then when you run your wort through or your mash through, you're getting better filtration as you go. Because when you do your first fill, you're going to see a little bit of a cloudy wort, and to get a good clear wort, you need to Vorloff for a certain period of time, and then you would run it back in and finally open it up and go. There's not a specific amount of time for the Vorloff. That's actually going to change based on what grains you're using, size of your press, total grain bill, what type of beer you're trying to achieve. Those will all change based on time, and that's something that, over time you'll get a good time from. But we always say that visual inspection is the easiest and simplest judge of wort clarity as you're looking at it. In terms of sensors for fill levels, there are not sensors inside the chambers in terms of the fill level. The way that you look at fill levels is you would work off of your tank, and you would pre-size the number of chambers in your press to make sure that for every bit of grain that you're putting in, you have enough space coming out. So it shouldn't be something where you're not going to buy a press that's 50% too big and then operate it and then judge it off of that. You would set your recipe, and let's say your grain bill is 1,000 pounds. You would make sure you have a specific number of chambers in the press that can handle 1,000 pounds, and then you would run your process until your tank is empty. So it's not something where each individual chamber has sensors for your fill level. It's more working off of the preparation of making sure that you have enough space in your press to handle whatever amount of grains that you're putting in there. So the mash, so this is a close-up view of how the actual mash will go through each individual chamber. So the cartoonish picture on the top, you can see there's a couple cylinders in the gray portion. That is identifying what you're looking at in the bottom picture in these weeping or these eye holes. So the way it works is the mash goes into each individual chamber. This picture at the bottom, the cloth is not on it, so it's showing you specifically what those holes look like. If the cloth was on it, you wouldn't be able to see the holes. So the mash goes in the center, it fills up the chamber. The mash goes in, fills up the chamber, and then as the mash goes into the chamber, the wort would slowly start going through the cloth, and then it would drop down into any of these channels that you're looking at the bottom, and then through these weeping holes. These weeping or these eye holes are connected to the outlet port in any of the four corners of the plate. And then those four corners of the plate are pushed back to that outlet. The mash and the wort are always constantly looking for the least path of resistance. So you're looking at it from a standpoint of the more you fill, the more you push. Your wort's going to come out at the easiest point. So sometimes, depending on how the airflow is going, it might come out more top, might come out more bottom, and go that direction. The Vorloff, as we talked about in the previous slide, that's shut off after the wort clarity is achieved. The question about the sight glass, that's typically the easiest way off of the outlet if you're looking at wort clarity. The wort, like we said, goes through the plate eyes and then into the corner returns, and then those returns take it to that central outlet in the grain tank. So as you're looking at this bottom picture, this is one corner of the plate. So in each chamber, the plates are going to have these little holes in all four corners. So that way, any way the liquid's going to try to get out, we're going to give it a path to get out of the actual chamber. So here's an overall view of that process flow again. So you can see in the bottom corner of the plates, there's the holes that are going to take it to filtrate. In this specific diagram, you can see that there is, in the first plate, there's the weeping or the eye holes in the bottom right-hand corner. And then if you go to the second plate, the weeping holes are in the top left-hand corner. So the reason we do this is every time there's a chamber, so if you're looking at the first grayish octagon there, that would be the filter cake. We want each filter cake to have a chance to spread its wort and separate in all four corners. So as you're looking at it, there should be, in each of them, there should be, as you're looking at it, there should be something that in each of the four corners, you have the option to get that wort out to the outlet center. So in terms of the filter plates, this is what is actually doing the squeezing. So after we've done all the filling procedure and it's completely full, we would supply the compressed air to the membrane plates through the manifold, and they would push the grain and squeeze out excess wort. So as you're looking at the first picture, this is very similar to the first picture we saw when we were explaining the anatomy of the filter press. The red circle on the right is showing you the actual hose connection that the compressed air is feeded into. And then the picture on the bottom is showing you what actually, when compressed air is fed to the plate, that's actually what the plate looks like. So you can imagine your grain bed is full and you apply the air pressure, the actual middle of the plate is completely expanding and pushing that grain out of there. And so that's in an open picture showing you what the membrane press actually does. So in terms of timing, the process flow and then the actual membrane squeeze, that's something that can be adjusted based on grain bill and beer style to give you the amount of wort that you're looking for and make sure that you're getting everything you need out of it. Also, in terms of pressures, typically speaking, the squeeze pressure on the membrane portion is anywhere from 0 to 40 psi. It's not something that you need to take to a really high level. And it's also, as I kind of referenced earlier in the presentation, it's not something that you need to take a specific CFM level for. We recommend the compressor have about the capability of 40 CFM. But it's not something that you need to have a consistent flow of 40 CFM. It's just something that you need to be able to fill up the squeeze manifold, and then holding the pressure allows the membranes to squeeze out. Optional sparge, depending on how you want to use the press, you can sparge just as you would in a regular system. You can sparge in two optional places, and there's also two ways to do it. In terms of where you would sparge, you can sparge with either a core fill, which would be right through the center, and you can also do it in the top left corner. There's advantages and disadvantages to each, but both of them are effective ways to get your sparge water in there to try to chase as much extra wort out of the system as possible. In terms of how you sparge, there's some brewers that have gotten really good results by actually saving maybe 5% of their mash and excess solution that's in the kettle and using that as their sparge water because they don't want to introduce extra water into the system, or using it in more of a traditional sense where you would hold a certain amount of water back and then actually run that through the press as part of the system. There's a lot of flexibility with the press in terms of how you want to run it. So it's not something that you're fixated on one specific orientation or style. The last part of it is there's no limit to how many times you can squeeze it or how long you can squeeze it. If you're getting a positive amount of wort out, you can continue to squeeze, or there might be a time cutoff point that you're really trying to hit with that you want to squeeze a little bit harder, get as much out, and then get to your next grain bill or next grain in or clean out or anything else. So it's really something that you can play with times temperatures, times pressures, and how much or how little extra wort you want to get out of the squeeze. Last thing is cleanup. You would, to clean up after you're done with your entire process, you'd remove the hydraulic pressure. By removing the hydraulic pressure, the pusher plate would push back, and then you would have the ability to move your plates around to actually see the grain that's on the inside. The biggest thing is getting the solids off the plates. Most of them will fall off on their own. The two pictures you're looking at, the picture on the right, that's the way a good cake should look like. It should be dry. It should be able to stay together. You should be able to use a simple plastic large spatula and essentially peel the grain right off the plate. That it should fall off in one big cake. Picture on the left is a picture of, if the cake's a little broken up, of what it should look like. It should be light. It should be dry. If you touch it immediately after use, it should be hot and a little bit sticky. But after it cools down, it should be very light, very dry, very easy to move around. The couple things we've found from this, you can store your grain after the press for roughly a week before you start noticing any sort of smells or things like that, depending on when you might need to get the grain out of your facility. And it's something that it's easier to move around. That an entire chamber cake, if it sticks together, should be light enough that you could pick up and hold and not fall apart. It's easy to clean. It really loses its stickiness because so much of the wort is out of it. It's an easy thing to work with. In terms of advantages, I have one slide here to really kind of touch on some of the different things we've found in our time of using the press in the brewery situation. Number one, flexible use of materials, whether it's high grain bills, alternative starches, unique additives. I saw a couple things in the chat about sticky mashes or things getting stuck. This is something that doesn't really have an effect on the mash press because essentially you can turn your pump speed up and really get it into the press, whether it's stickier than normal or you have something unique in it. That's something that's a real big advantage of the mash press over a traditional system. Second one, consistency. There's a low variety in the results because you're manipulating the mash so well as part of it. And the lautering times are really predictable. You're not really worried about conversion times changing or things going on because you're putting it in there, you're running, you're pumping, you're running your squeeze, and you're getting the wort out exactly when you want, that everything becomes a lower variety and more predictable. Extract potential, typical is 98 plus. We do see several of our customers that have been using it for the 7 to 8 years since we've really gotten into this are in the above 99%. When they do lab analysis of the unit, they're typically 99 to 100%, if not higher, when they do a lab analysis of it. The one thing that people kind of forget about is there is, some liquid in the grain just by nature. And so when you put it under pressure and you squeeze, you're achieving and getting that liquid out of it as well. Easy cleanup is another one that really makes a big difference. You should have 70% plus dryness on your spent grain solids. It should not be sloppy or sticky, and it should be able to be stored on site longer prior to any sort of smell or odor that would keep you from keeping it inside or anything along those lines. In terms of savings, you can run it, the press essentially two different ways. You can run it identical to how you would for your barrelage size, your brewery. So let's say you have a 10-barrel brewery. If you want to run it with those same recipes and everything else, when you squeeze, you're going to get a much higher amount of extract out of it. So you would get a bigger or a larger amount of wort for the typical setup that you're using. Or if you're trying to specifically get 10 barrels out, you'd be able to use less water and less grain to achieve that same amount. And then the other one is less manpower, specifically from a cleaning standpoint. Most of the units that we sell, unless you're getting into a really big one, is something that one person is strong enough to move the plates around, scrape the cloths off real quick, and then use the hose to clean it off. It's not something that you should need 4 or 5 people working on as part of your brewing operations. So I'm going to turn it over now to Kevin and let him talk about controls and integration of the press.
Okay. Thank you so much, Trey. And yeah, I'm going to just saying a quick hello here. I'm going to just talk a little bit about the controls and integration. One of the things that we've been working on alongside with MicroPure, excuse me, is how to integrate this properly, how to integrate it with, control panels, whether it's a standalone control panel that would work with the press, or if it's integrated with an existing control panel. For example, our advanced control panels, we could hook up a module to it, and that module would still be communicating back to the touchscreen, but it would be the hardware that would control the press. So there's a lot of different options out there. That's kind of how we handle it. But I'm going to go ahead and talk a little bit more on the next only 2 slides here. So there's quite a few things that you could do for automation. One of the questions that popped up and I answered on the sidelines is the use of a pressure gauge. You see that in the upper right-hand corner. We do put a pressure gauge on the input side of the press, and we're looking at monitoring what the pressure level is, the back pressure, and you can dial that in to know when your press is getting full or just about full. And it becomes really important, especially if you're using, a different positive displacement pump, et cetera. If you're using a diaphragm pump, they pretty much self-regulate. That's kind of our recommended way to go. But we do use that back pressure. So a little bit more information on that. We also integrate automatic valves. So if you see the left picture up on top is a, I forgot to take my camera off here so you can see a little bit better. Motorized butterfly valve. So we utilize that after we fill the press. We'll close that valve so that when we do the squeeze, we're not getting any kind of back pressure or backfill back into the mash tun. And so that's a nice way to handle the controls on the input side. We also take a look at what the process pressure is, and also the plate pressure. So we'll get a signal back from the system saying that the actual filters are squeezed together properly, because the last thing you want to do is feed in and forget to close the filter plates. So a little bit of a level there of safety. On the output side, what we do is integrate a grant, an auto grant, because as you start pumping through that press, the beginning runnings are coming out very fast because there's not much resistance in the filters. So we go right into a grant. We have the level sensors in there. So as soon as it hits the level sensor, it starts transferring either to the kettle or back to the mash tun if you're doing some boil off. And that could be automated with valves as well. And then as you go, it's going to be a lot slower toward the end. And again, it's just making sure that the pump that's taking away the wort going into the kettle is not running dry. So that's what those grant level sensors are about. So yeah, talk a little bit more, on the integration side of things. Just a couple of pictures of some integrations that we've done. Top left is a 10-barrel system that is actually, they're getting a lot of capacity, so it pretty much can act as a 30-barrel system because you can make 3 turns of batches at the same time. You could do 1 turn. Also we have customers on the smaller side, up until here recently, the filter presses were typically used on the bigger breweries, but the craft breweries and smaller breweries are really starting to find some value in the press, not only for turning a small brewery into a higher capacity, because if you could triple that capacity, obviously that's a huge advantage, but also putting in a various grain bill that typically would cause issues with stuck mashes, et cetera. I saw some comments on the side about that. So with the integration, there's some different pumps that you could use. Say an air-operated diaphragm pump that will definitely increase the size of your compressor, so something to keep in mind. But that's kind of the easiest one. It self-regulates. You could hear the pump pushing the mash into the press. You'll hear it start to slow down, and even if you're not paying attention, or if we don't have the pressure as the automation, it'll just stop pumping because it just can't pump anymore. It's not going to do any damage to the pump. So it's a nice, easy way to go. Impeller pumps are another solid way to go. A little bit of a drawback is the wear and tear on the actual impeller. Regular centrifugal pumps have been used, a little bit more tricky to do, but they can certainly move the mash in through the press. Low pumps, progressive cavity pumps, positive displacement ones, those you have to be a little bit careful because they could generate quite a bit of pressure going in. So you definitely need to do some automation there. So yeah, just a couple of pictures. Actually, the bottom left is one that we did in a little bit of a different application. But that's John, who is part of our staff here, standing next to it. So they can get pretty large, but typically the ones that we're doing are a lot smaller, like you see in the other pictures. All right, so I see some questions coming up, so I'm going to kind of hand this back to Trey unless there's some controls, and I'll put my video back on if you want to as well, Trey. Yeah, what kind of questions do we have?
The one question I saw here on the stringency, when you're going to end up milling your grain to specific mill specs. So that's not something you shouldn't see. You shouldn't have any extra stringency just by using a press. I saw in the comments someone talked about one in Minneapolis. That's a Mura. They might have different recommendations or different process flow from what we would tell you to do in terms of your mill specs or what type of mill to use. And so they might have a different answer for you on that. The other thing I would touch base on too, we always get a lot of questions about whether or not the press is going to cause tannins. That is a urban legend, myth, however you want to phrase it. Tannins are really from excess temperature and excess heat, or not. Excess temperature is really the biggest one that gets it, and you're not putting it through that. And you're also not exposing it to any sort of sunlight comparative to what you have in a tank. So there's no extra possibility of tannins by using a press comparative to what you would use in a traditional setup. If there are any other questions, I'll be happy to answer them as we're sitting here.
Yeah, Dan Franklin asked about the mill and whether pre-milled grain or the type of mill. And I mean, on our side, I know we typically doing a hammer mill instead of a roller mill, but maybe Trey, you could answer a little bit more on that one.
Yeah, I think the mill is a very similar conversation as what Kevin brought up with the pumps. Typically speaking, we think a hammer mill works a little bit better. The more floured the grain is, the easier it is to fill your press. But that's not to say it's not going to work with different levels of milled grain or pre-milled grain. The one distillery we just installed in the last 6-7 months, they're operating very well using pre-milled grain that they get coming in, and they get it put at whatever mill spec they need. You can play around with the mill spec to get different possible efficiency levels. In the research we've done, we've not seen a specific mill spec create a better efficiency level, but it's something from brewer to brewer. They have their own idea on what gives them the best fill, best efficiency, best conversion.
All right, someone asked, how long does the process take compared to a similarly sized mash in a non-mash press brewery? Kind of my 2 cents, yeah. My quick 2 cents on that. I'll let Trey answer specifically to the mash part of it in the press, but there's some things that you could do on the integration side to speed the process, such as having a separate whirlpool tank along with your kettle, because you might be you'll certainly be able to push through faster than you're going to go through a boil. So there's even some folks that would use 2 boil kettles to really speed up the process. So keep in mind that there's a lot of other integration perspectives out there to really push some volume through. But Trey, go ahead and answer a little bit about the regular press time frame.
I would say in terms of the time frame, just going off a 20 barrel system, mash in to completely done should be less than 40 minutes. And every bit of a smaller press or bigger press is going to kind of vary from that. We specifically don't have a lot of experience brewing on traditional systems, so I'm not totally sure how long a 20 barrel system would take to go through lautering, filling and lautering. But that's something that from our standpoint, we normally tell people 30 to 40 minutes is kind of the 20 barrel time. And then realistically, you're kind of getting, shorter below it. And then you're getting a little bit longer after it. Honestly, the longest portion of the process is filling, because you have to make sure you fill all the plates, and then you might have to do a recirculation for a little bit. But it's not something that the actual squeezing shouldn't be very long. And then the clean out time is really, really short, particularly if you're doing multiple brews in the same day.
Yeah, we've done batches in our test lab here on the smaller filter press. It goes pretty quick. It's a 2 barrel system, so we're able to push through a batch, certainly less than 40 minutes. All right, Trey, the elephant in the room. Someone asked about some typical pricing. Obviously, that can vary on the size, but is there any insight that you could offer on that?
Yeah, I mean I guess when you're thinking about the cost, it's twofold. The first, there's obviously going to be a investment cost right away that you're going to have to put into it. That I don't have my price sheet in front of me that I can go off of. But what you're really looking at as part of this is there's very little upkeep costs that you're going to run into, that you're going to be replacing costs maybe 9 months to a year, and that should be a very low cost. But it's something that you're also thinking about too, the excess wort that you're getting out, and the savings you're getting in terms of water and grain should really make up for what you might be paying up front to get the piece of equipment.
All right, Trey, I don't know if you see the question from Tiffany about the cake causing combustible dust hazard.
No, there shouldn't be any sort of dust hazard. The cake sticks together pretty well. The only way I think you could possibly have a dust hazard is if you made it such a fine dust and flour when you were filling that you might end up with something along those lines. But even still, there's still enough liquid or moisture in your cake that it should be sticking together. This isn't something that when it comes out of the unit, it should be turning back into the flour that it started. There's still going to be a moisture component to it. So it's not something that you should be creating excess dust from it. How loud the system is when it's in operation. If you use a diaphragm pump, there's a decent noise to that. But it's really no different than any other air compressor or air unit being used. If you have compressed air in your facility and you hear the noise from that, that's really kind of the air you're going to hear out of the system. Typically speaking, when you're using the system, the loudest noise is when you're closing the press, because the oil very quickly is going to the pistons. That might be kind of loud right away, but in actual operation, it's not like you should be hearing loud hammering, banging, or anything else from the unit. It shouldn't be a noise hazard to workers. There might be a 5 to 10 second period where the hydraulic unit is loud, and then when your pump first starts going, it's going to be loud, but it's no louder than any other pump. So it's not something that would really cause you any issues.
All right. Jeff has a question here. Process changes with grains.
In terms of alternative grains, there really isn't any process changes. If you're talking specifically about sake, the two changes that are made, the first is the cloth is a lot tighter. And then the second is the squeeze is longer. The rice absorbs liquid at a much higher rate than the typical brewing or even distilling grains do. So it doesn't come out as easy. So it's something that the process time is a little bit longer, but it's really the process time that's longer is the squeezing. The actual feed portion, honestly, is identical, and then you just end up squeezing it. Of the couple different sake facilities that we've done, some of them are squeezing for up to 24 hours to really get every last bit of liquid out of the unit. But it's something that from an actual like step-by-step process isn't any different.
All right, I believe we got to all the questions. If you have any other ones, we still got a couple minutes here, so pop them up. But in the meantime, you might have seen a schedule one-on-one pop up on the screen. We set up on the vBrewCon website that you can go ahead and schedule some time with any of the panelists. We're all carved out time to be down in Texas this week, and obviously we're not. So we have time and would love to chat with you. I know there's some questions on pricing. We could look at the size brewery that you have and give you some budgetary numbers, chat about your application, things along those lines. So feel free to click on that, and you should find Trey, myself, and others from our staff as well. So go ahead and click on that, and if you think of it later, you could always go to the vBrewCon website to do that. And also, we have the replays as well on the website. So if there's something that you missed or something that you want to go ahead and focus in on, please go to the website and check that out. It'll be recorded. And doesn't look like we have any other questions here. So we thank you so much for being here with us. I know it's real early for everyone out on the West Coast, but thank you so much. And Trey, great job. I appreciate all the knowledge that you gave us during the presentation.
Yep, no problem. I kind of want to echo what Kevin said, that, if you guys have any additional questions or want to see some more information or drawings, pictures, anything else, I'll be happy to help out with that type of stuff and kind of go from there. The biggest thing that we've run into as we've been doing this, so it's so common to deal on a typical tank system. The mash press is something that's new and different from a craft standpoint. And so it's something that if you haven't done it before, there's always a little bit of nervousness jumping into it. But we have enough experience that if it's something you're intrigued by, feel free to reach out to Kevin or I, and we'll be happy to help kind of get you organized and give you help going in that direction.
All right. Excellent. Thanks again, Trey, and thanks again, everyone. Hopefully we'll see you at some of the other seminars.